Can people hear this? Can people hear this? Can people hear this? Okay, so I think that if it's okay with everybody, I'm going to go ahead and start the stuff right now. If you have any questions, just type it to me in the comments, but just note that YouTube Live has a delay, so I might not get to it for a few minutes. Or seconds, I mean. So let's start at the beginning. So this assignment is called Assignment 3, Base Nets. I'm Dan Scarafoni. I'm the teacher's assistant who is going to be doing this assignment. So without further ado, let's get started. So basically what I'm going to do is I'm going to go over the assignment details and then the assignment setup. I'm going to tell you what files are in the project, how it's going to be evaluated, and then we can do a Q&A where you can ask me questions. So the assignment was released on June 8th at midnight. It's due on the 21st at 11:59 p.m. and it generally covers modules 5 and 6, I'd argue. It's largely about it contains some statistics, which is why I include module 5 in it personally. So what's in the assignment? So the goal of the assignment is to work with a probabilistic model called a Bayes network to calculate probability questions about random variables. And we're going to release a bonus part on variable elimination, which will be due on the 28th. And more info will come of that in the coming days. So what exactly do you do in this? The gist of this assignment is that you're going to create a Bayes network, and then you're going to answer a bunch of problems about the Bayes network, and then after that you're going to implement Gibbs sampling on that and Metropolis Hastings, and you're going to use that to generate probability, basically random variable samples, and you're going to use that to make inferences about it. The details are shown on the screen here, where you want to assign a Bayes network for a model, and then calculate the conditional probabilities for that, then calculate inferences. Then for the second part, you want to build the network for that question, calculate the posterior distribution to match some probability questions. Then you want to implement Gibbs sampling, Metropolis Hastings, and just analyze basically the probability of different outcomes, which is to say to estimate the total probability distribution of that network. And there's also a point there for writing your name. Let me check if there's any questions. Okay, so basically, how is this project? Oh, I'm sorry, this shouldn't say Jupyter on it. So this is very much similar to what you've done in the past, where you have a assignment and you want to get a Python environment set up and then run it. Now, one thing that I should tell you is that we had to change the requirements file. It previously just said to install PyTorch. There was apparently an update to PyTorch that made it not interact with Torch Vision. It should work as is, and if it doesn't, there's a thread on Piazza that you can use in order to work things out. And of course, the TAs for this project, me and Michael Johnson, are on Piazza, so feel free to reach out. So there's two files in this folder. One is submission.py, which obviously contains the code that you write. You have a local unit test file, which you can run if you want. I will probably just put a brief thing about how unit tests work in Python, because I've gotten some students who don't quite understand that. And I just rather save you the pain of having to learn it yourself. It's like one line of code to work it, and it's pretty elegant, I'm not going to lie. So how are these evaluated? So basically you test it locally with your probability test to see if it's working. Now for GradeScope's also a series of unit tests. It's basically a large chunk of how well you set up your network and are the probabilities right. And as is highlighted in big letters at the beginning of the assignment, you only get 5 chances for this one. That's done to prevent people from brute forcing the algorithm. So use them wisely. Okay, that's really all that I had to go over with regards to this assignment. We can use the rest of the time for a Q&A if you guys want. Okay, according to my YouTube live stream, there are 7 people watching this. So if any of you have questions, just put it in the chat. So as to whether or not the unit tests, all right, so the first question I'll answer is Jay's. And Jay's question is, any advice on strategies for testing? Will the unit tests be sufficient for this? I can't say definitively, although the unit tests are pretty good, and I can tell you that if you want to, basically most of this assignment is just going to be evaluated on whether or not you got the probability correctly. So this is actually really easy to make unit tests for yourself. You can make your own unit tests, sampling it, and if you, sorry, I just got some notifications. Basically, if you have you can create new unit tests and you can test it, and these will be things like, let's say you're trying to evaluate Gibbs sampling. So one thing you could do is you could, after your Gibbs sampling burden period, you could make a unit test that will evaluate the probability of 10,000 different poles of the probability distributions to make sure that they're within what you would calculate. A lot of this can be calculated by hand, which is really, really nice, because that means that you actually have kind of the answers beforehand, so long as your math is good. I contrast this with assignment 1, where you have to beat an AI that's dynamically changing and you can't really determine whether you're going to be right or not before you do it. So you have a lot of play with this, thankfully. That's also one reason why we felt more comfortable, saying that people only get 5 shots. So the next one is by Cara de Freitas Bart, and she asks, can you talk more about the finding CPD? I think that's conditional probability distribution tables for a node that has 2 conditional nodes. Yes, I can. So for this one, it's probably easier actually if I just start to draw, honestly. So I'm going to run through this example and then I'll come back and check the chat, but feel free to just type stuff. I'll guarantee you I'll read it. Alright, so is this good? Oh, what is this degeneracy? Alright, you know what? I don't like learning new things because new things can hurt you, so I'm just going to go ahead and edit this safe thing. So I'm just going to make a simple Bayes network with 3 nodes. You have node A and B. And then they are parents to node C. Now, as we can see here, let's see, you were asking about, 2 conditional nodes. So I'm assuming that you're asking just about how probability works in this case and how you would find conditions. So this is actually a really common question that we get, and it's, how do I put this? It's not only that it gets a lot of, that the probability distributions get really, really big very quick, it's also that you kind of want to, the actual algebra of conditional algebras, the algebra of conditional probabilities gets kind of unintuitive and weird. So for example, if you have one parent, let's say B, then let's say that each of these are binary, they can be true or false. Let's say that, so in that case, you can have C is true or false given B is true, and C is true or false given that B is false. So for each value of B, you have 2 values of C, which is 2 times 2 is 4, so that's 4 total entries. You can simplify things a little by only giving the probability for C is true, because you can just, 1 minus that, and that's your previous, either that's the other conditional, but, realistically and technically it's 4. And if you have A2, then what's the total number of combinations you have of A and B? Let's see here. There are 2 times 2, so that's 4 different ways that the parents could be arranged. And then for each one of those, you have 2 values for C. So that's 8 total, and this increases exponentially. So if you have 4 or 5 parents, you can have really, really big probability tables that are terrible to calculate. Now, thankfully, one of the things that Bayes nets actually are great at is they can abstract this away. So that basically Bayes nets allow you to have conditional probability. So for example, if instead of A being C's parent, if A was B's parent, see, this way you only have to calculate a table of B given A and C given B. And this will drastically cut down on the total number of how big your probability table is. But let's talk back to this point. So let's just say that we're talking about the value for C is true. And we have 2 values A and B, so let's see, true, true, false, false, true, false, true, false. Basically all the different probabilities that we could have. And let's say this is 0.3, and then this is 0.2, 0.1, and 0.8. And obviously the probability of C is false given these 2 would be 1 minus this value here. Now, in order to find, let's say that we didn't know what these values were, and we were just trying to find out, what they are. So, in this case, let's see here, how do I describe this? Let's say that we're given a whole bunch of, let's say that we're, in order to fill out this probability table, let's say that we're given a whole bunch of data. So our data is basically all the we sample a bunch of Bayes. We look at this Bayes net a whole bunch of times to figure out what the distribution is. So let's say that in this case we would have, let's say a bunch of data, we're getting a bunch of data points and what the values of these are. Maybe true, 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 false, true, false, true, false, false, false. Now this is just a series of 2, 3, 4 times we've looked at the data, and we're trying to figure out, and let's say we're trying to build the total probability distribution from all this. So the first thing to calculate, which is the easiest thing to calculate, is what's the probability of, A being true and B being true, since they don't have parents. Well, in order to do that, you just count. So A is, let's see here, 1, 2, 3, 4. 3 out of 4 times it's true, and the 4th time it's false. So from this, the probability of A being true is 0.75. And B is, let's see, the probability of B being true is 0.5, and the probability of being false is also 0.5. Now, remember, with C, we want to calculate this based off of the probability table, and remember, it's conditional. So what that means is, if we wanted to calculate the probability that C is true, given that A is true and B is true, we count all the times that we find A and C to be true, A and B to be true, and we see how many times that C is true, and that'll give us our number. So in this case, we have, let's see, we have 2 main data points that we can look at, this one and this one. And because in both these cases A and B are true. And we have one sample where C is true and one where it's false. So the probability of C being true, given that A and B are true, is 0.5. And you would similarly go through this table in order to learn these probabilities. It's tedious and it's a lot of hand working, but this is how you would calculate it empirically. So the next question is by Jay again, who asks, want to invest some time up front in testing due to the submission 5 limit. Oh, is that just a follow-up to your previous comment? Oh, okay. Cool. So, all right. Anyone else have any other questions? So Jay asks if we have any advice on timelines for the project on when we should have each part completed by. I don't have any advice personally, but I can tell you that if you look at the assignment details, I can tell you that 1A and 1B, 1C, 2A, those are all pretty simple. Those are pretty much what you see is what you get. As in, there's not a lot of hard math or algorithms behind it. It's really just it's almost more coding than anything else. So if you're calculating the posterior distribution, that's when you have to know the posterior calculation that is similar to what I just did. So that if that that itself is simple, but the concept behind it, some people have struggled with. So you have to gauge for yourself how hard it is. Now, on that note, Gibbs sampling is significantly a lot more difficult than the other parts. and Metropolis Hastings is that's even more challenging than Gibbs sampling to implement. Just because it's got some more arcane mathematics. But once you get those two implemented, 2E is not gonna is gonna it's gonna flow fairly easily. So yeah, I think that should give you a. I would honestly encourage you to test the waters to see for yourself how long it's going to take for you to do stuff. Okay, next question is by Harshita Bandlamudi, and which is, if A and B are conditionally independent given C, how do you calculate the probability of B given A? So the probability of B given A in this case is just the probability of A, and we can look at this actually with Bayes' rule. So let's say that we're trying to. Let's say we're back here, and we're trying to calculate the probability of B given A, which is equivalent to the probability of AB times the probability of, actually it's just this divided by probability of A. So this is equivalent to, because we know that A and B are conditionally independent, which is to say the probability of, or B and A given A equals probability of A times the probability, because this is just what it means to be conditionally independent. So we can safely say that this is probability of A, B times the probability of A, which is equal to probability of B. So yeah, it just follows from conditional independence. Oh no, I'm sorry, you're asking for a different scenario, aren't you? You're asking if C is the parent node and A and B are the child nodes. Alright, so in that case, so the question here is, how do we calculate the probability of B given A? Right. Now, in this case, the one way that I would think about it is actually marginalization. So let's see here. What this is now what this is equivalent to is equivalent to B divided probability of A. B and A. So this is equivalent to, I'm going to just give the summing over C notation of the probability of A, B, C divided by probability of So you can obviously decompose this into the entire Bayesian equation, so that'd be probability of C times probability of A times C times probability of B given C. And that'll get you, and you can do likewise with the denominator, and that will get you this end probability right here. Here, I'll write that out for you. So that's how you would solve that. Does anybody have any other questions? Okay, well, if nobody else has any questions, and I guess that concludes this YouTube live stream, I'll have it posted to Piazza soon. And thank you all for your time. Have a good day.